Saxon Algebra 2, Lesson 64. Greetings, students. We have two delicious algebra-related topics to cover today. No fuss, no muss, almost no words, although plenty of letters. Just super straightforward two-part lesson. The first part is on complex fractions, and I'm just going to tell you right now, the second part is complex numbers, which I just find two delightful titles. All right, we have done complex fractions before. We're just gonna up our games a little bit and make them, I mean, I'm sorry to say it, but a little bit harder. A little bit more complex. Write the following as a simple fraction. Here we go. This is copied exactly the way John has it. You'll notice the floaty here. You can see what's happening. This is getting complicated, and then we're adding a random thing over here. So how do we know where to start? Again, we go to what looks like the innermost part of the problem, right? The denominator, we want to change into a 1. And we look at our denominator here and we go, oh, what are we even going to do with this? Well, what we have to do is we have to, in the immortal words of Evie Jones, one of my students, we have to smush these two together, then we can flip them. So the strategy that we're using here is called the smush and flip. Okay? So we're gonna smush them into one fraction, then we'll flip. And look, I've used up my space by writing that title. Oh well. Okay, so we're gonna put this over a 1. Now we can see, okay, to put these with matching denominators, we're gonna have to multiply this one by b over b. I'm just going to turn that into a b, right? Least common multiples of b, obviously. So this becomes 1 plus bx over b. Beautiful. Okay, now it's smushed. Now we can flip it. b over 1 plus bx. And then we have to multiply, this is the reciprocal, so we have to multiply this by the same thing. b over 1 plus bx, okay? I feel good about this. This has turned into a 1. So what I do is I just draw a line through the whole thing. We turned it into a 1. Once we multiply by the reciprocal, we know it's all good. 1 denominators disappear into thin air. Thank you, goodbye. So now we have this as our next step of what to do. Now, sometimes it helps students to imagine this first thing as a fraction so we can multiply across. When we have more complicated things here than just a plain old 1, that will become especially true. So I very often put that over a 1 just so I can see how my multiplication will work. I'm going to recopy the whole problem. The numerator is b. The denominator is just 1 time, so it's 1 plus bx. Okay, beautiful. I'm getting close to the end. I just have to smush these two together. So in order to do that, I have to look at my least common denominator. I see it's a quantity. I'm going to have to multiply this by 1 plus bx over 1 plus bx. I can put this over a 1 if that helps me. It's a little smushy, but you see what I'm doing here. And then this I will put in a quantity parenthesis so I can multiply that. It'll be a times the quantity 1 plus bx plus b, and the whole thing is over 1 plus bx. Remember, we cannot cancel these because this is being added over here. And so, no deal, we can't cancel there. What I can do, though, is distribute. And so that will give me a plus abx plus b over 1 plus bx, and guess what? We're done. Okay? So we took something that looked, I mean, it's hard to even see the original problem, something that looked like this, and we turned it into this. Some students would ask, how is this simpler than that? I know, they're both kind of crazy. The difference, though, is that this one, everything's together in one single fraction, whereas here we had a bunch of fractions within fractions, and then this thing hanging off that wasn't connected at all. So at least here we put it all into one big ball of deliciousness instead of having all of this craziness. All right, we have one more, and then we're going to switch topics. Ready? Flipping. Example 64.2. And here's this one. I find that these problems are easier for me to work if I give them a lot of white space so that I can multiply things and squish them together. Now this one, it looks sort of the same, but also sort of a little different. All right, so there are different schools of thought on how to approach this. What I like to do, again, is I look for the most complicated denominator and I start there. I'm gonna work on this fraction until I get it all cleaned up, then I'll compare it to this one. Some people like to kind of start working on both at the same time. No, that's confusing to me. This is the messier one. So let's start here and stay here, all right? I need to smush these, right? We got the smush and flip going on. So in order to smush these, the denominators have to match. This is an x, so I'm gonna multiply this one by x over x and turn that 1 into an x over x. This becomes then, I'm gonna change the order, b plus x, I can change that order, over x. And now I'll multiply by the reciprocal of x over b plus x. And all of my problems have gone away. I'm gonna slash through that, but this reciprocal needs to come up over here. X over b plus x. Again, I can put this over a 1 if that helps me. I'm now ready to rewrite a over x plus 4x over b plus x. Got it? 4x, 1 times b plus x is b plus x. All right, good. Now we can turn our attention to putting the two of them together. This is as clean as it's gonna get, so now we're gonna squish them. Least common multiple. Oh man, these are still so tricky, you guys. This is a quantity. We cannot make this x match that x. We cannot turn our least common multiple into b plus x. It won't work. It's so annoying. That's why I like to call it the least common multiple, because it reminds us we can only multiply to build these things. So x times the quantity b plus x. All right, so now we're going to multiply by the missing pieces. This one is missing the quantity, so I have to multiply both sides by b plus x. Oh my gosh, I almost choked on my words there. Right? We multiply by the missing pieces so that each denominator becomes the LCM. This one, we're missing the x piece, so I multiply by x over x. Right? I'm going to put parentheses around just to show multiplication. All right, let's see what we've got here. A times the quantity b plus x plus 4x squared. Oh, interesting, right? And then our denominator is x times the quantity b plus x. And I think I've talked about this before, but John's style, this isn't wrong. This is perfectly right. John's preference is to distribute the top and leave the bottom undistributed. I kind of like that. I like to distribute the top because you never know when you might find some terms that match, and you can simplify by adding like terms. So I like to just go ahead and distribute the top but leave the bottom. So AB plus AX plus 4x squared, that remains unchanged, all over x times the quantity. Oh, I just changed the order of it, but that's fine. That doesn't make any difference, right? X, I'm just checking my answer to make sure it's right. Yes, this is right. Again, if you gave me this answer on a review problem or a test, I would either accept it or I might hand you your paper back and say, distribute for me. But this isn't wrong. This is just stylistically maybe a little bit more delightful. I don't know. If you can follow this at all, you're doing a great job. These are very difficult problems, and I'm impressed if you're hanging in there. All right, that was complex fractions. Let's go to our second topic, squeaky chair, which is complex numbers. Oh yeah, complex numbers, what do we know about them? They're this a plus bi thing, where this is the real part, and this is the imaginary part. And we have a couple simple things we remember about imaginary numbers. The square root of -1 is how we get imaginary numbers, right? And then the other thing we know is that if we have two i's, that equals -1. Two i's sounds like, you know, the i's in our heads. I meant two imaginary numbers. If we multiply two imaginary numbers together, we get a -1 of a real number, all right? So there is a link between the systems. All right, and then this, we want to remember this. So these are the facts we're bringing to this new topic on complex numbers that we already know. And just to drive home the point, if we have this is not a real number. We can't find that on the number line. But what we do is we split that apart into 2 times -1. And then we split them, if we really want to be deliberate, we split them into separate pig houses. And then this can be written as square root of 2i. Notice that the I does not live inside the pig house, right? It stays outside. Okay. 64.3 is the example we're on. This goes up to 6, but these problems go pretty fast. Simplify square root of -2 times the square root of -3. Here's what we do not do. We do not multiply these together and say, oh, look, it's the square root of +6. No, can't do it like that. What we have to do is rewrite as complex numbers first. So we change this one to 2i, right? We went through that right here. And then this one, the same thing. This would be square root of 3i. Okay, so then this becomes square root of 6. We can put those two pigs together. Square root of 6 times I squared. But look, I squared is equal to -1. Not in a pig house, but just a plain -1. So that means we rewrite this answer as minus square root of 6. It's all very mind-boggling. And if you try to logic through this process, you'll probably hurt yourself. This becomes a -1 outside the pig house. All right? I don't want to squish. Sometimes I think, I can fit that problem in, and I always regret it. So let's go to the top of the next page, because, you know, life's too short to have regrets. 64.4. Oh, it's one of these. Ready? 4i cubed minus 2i to the 4th. I don't have to say it out loud, do I? Okay, I'm going to write down my rules again. Square root of -1 equals I, and I squared equals -1. Those are our two carved in granite rules that we use for complex numbers. So here we can use the fact that this represents 3 i's. 2 of them can turn into a -1. So we're still going to have the 4i. There's 1 left over, but 2 of these turn into a -1. And so we have a minus sign there. Now here, we've got 4, so that's going to turn into a -1 times a -1. That's a +1, and that means this isn't changed. These all get used up, turning into -1s, but the 2 of them cancel out their negatives, so this just stays plain 2, right? The sign doesn't change because these guys come to a +1. Okay, ready? Now, the first thing we do when we see a minus sign in a pig house is we get that turned into an I. So this becomes square root of 9i. Square root of 9 we know is 3, so then we'll multiply 3 times that, and we'll get plus 6i. Whoa, these are tricky complications, aren't they? Or simplifications. Then here, we're going to change both of these. This will be square root of 3i, square root of 3i. We always convert these to complex or to imaginary numbers first before we simplify. We don't multiply them together. So these two 3 pigs will come out to make a regular pig, and these two i's will multiply together to make a minus. So it's going to be minus 3. That is a lot, you guys. That is such a lot. Those two 3's make the 3. Those two i's make the minus. It turns that into a minus. All right, we got through the worst of it. Now all we have to do is put this together into a plus bi format. So first we'll do the real numbers. They're minus 5. And then we'll do the imaginaries. And that becomes what? Plus 2i, right? And that's our final answer. I didn't add the third piece of my knowledge trifecta on complex numbers. We always want them to be arranged in this format. It's a big deal. We want to keep them separate. We would never like put a fraction with the same denominator for both because these are such different realities, right? This is a real number and this is imaginary. We want to keep that division really distinct and clear. And every once in a while, we'll have problems where we could let them share a denominator, but no, we never do that. And that's why I've told you that with radicals, we sometimes have the same thing where we could let them share a single denominator, but because we like to keep our complex numbers, our imaginary numbers, so separate, we do the same with radicals usually. It just is it's a more clearly indicated difference. Okay, 64.5. This looks like it might be hard, but it's a familiar friend. This time we're asked to multiply. And we have two binomials that are complex numbers, right? Real, imaginary, and we're supposed to multiply them. Lord have mercy, how do we do it? Well, here's the thing. It's very familiar. We're going to take this and we're going to write it underneath, right? Just copying it down there. And we're going to do the dance, just like we do the dance with other numbers, a lot of times with radicals. We're just going to multiply, right? This is the first girl. She multiplies. These are the boys. These are the girls. First girl gets to dance with both of them. Second girl dances with both of them. We add up all the pieces. Okay, here we go. 3 times 4 is 12. 3 times 2i is 6i, right? It's okay to multiply a real number times an imaginary. You just multiply, you just go straight forward. Now she's done, her turn. Minus 2i times 4 is minus 8i. And now here's where it gets crazy. Minus 2 times positive 2 is negative 4, but then we have I squared. So this turns into a negative 1, and it turns this into a positive 4. That's a lot. Looks so easy when I do it, right? Okay, then the 4 can be added to the 12, and we get 16, and then we get minus 2i. 16, yeah, it's minus 2i. I was looking at my notes from last year and realized I made a mistake. Maybe I changed it. It's supposed to be minus though. I did it correctly. Yay! These are all correct. I've been out of the game. There, I got a smiley face back there. Okay. Whew. Hate to see it, don't you? All right, one more. Example 64.6. It's the same as last time. It's a pair of binomials that represent a complex number. This time, John wrote the first one in a way that looks odd to me. He put the I first, the imaginary part first, and then the real number. If you want to, you can fix that so that it will look the way it's supposed to. And that's what I would try to do. But if you forget and you just copy down the problem like this, it'll still work. Okay? This, though, after you get a little more experience, you'll realize, it just sets your teeth on edge to see it like that. And I would change it to -2 plus 5i, right? So that it's got the proper formatting, and then multiply it by 4 times 3 plus 3i. This looks better to me. Actually, you know what? I should make this hard eyes. This is okay. It's just got a little smile. This is better, but we're going to do it this way just to show you that it will work just fine. Okay, ready? 4 times 5i, 20i. 4 times -2, -8. She's done. Her turn. She's a girl. 5 times 3 is 15. And I'm not sure where this is going to work out. I squared, right? It's positive. But this turns into a -1 and turns this into a negative, right? And then last one, this is -6i. So I'm going to write that here by my other I. Oh, again, that sounds so weird. Then when I write my final answer, I'm going to make sure I get it. Well, here, let's just do this. This would be 14i, and this is -8 minus 15, that's -23. But we cannot leave the answer in this format. This is wrong. It's -23 plus 14i. Always, always preserving our A plus BI dream state, right? That's the right answer. Don't ignore that. I was trying to make a puffy cloud around this, but I was wrong. Yay! All right, so there is a little refresher and a little few bumps forward on complex numbers. Again, I want you to take a certain amount of satisfaction in realizing how smart you are. Because look at that, complex fractions, complex numbers. Oh, it's so hard. And look what's gonna happen to us in the next lesson. Advanced substitution. Man, we are getting so polished, such expertise in our lives as mathematicians. I want you, and I'm sort of goofing around with that, you know, but seriously, are you kidding me? Look at how hard these problems are. And you may be struggling and, you know, gnashing your teeth a little bit, but if you're even understanding at all what in the heck I'm talking about when I explain these, you're doing a fantastic job. Remember, you have to hear something 7 times before it really sets up housekeeping in even your short-term memory. 7 times. That's why I repeat myself. You know I do. That's why I do so many problems, right, of similar things. That's why I always go back and remind you what we already know on a topic so that you'll have it in front of you. That's why I try to start each lesson with a recap of what we already know. That's going to make it easier to build. Our brains do not remember things the first time we hear them. That's just the reality. The other tidbit that, I think it was Algebra 1 I was telling this to earlier in the week, it takes to move information from our short-term memory to our long-term, it takes 10 years. 10 years. So think for a minute. How old were you when you earned your multiplication times tables? I'm guessing 8-ish, 9-ish, 10-ish, somewhere in middle elementary school. I was in 3rd grade when I learned mine, so I was 8. And that means that when you're in high school, the 10 years that it takes to bump those things into your long-term memory, you haven't had 10 years yet. It's been less than 10 years. So students who need to think, students who need to count out with their fingers, who need to do mental addition to try to get their math facts down, I am 100% fine with that because you haven't had your 10 years yet. Parents sometimes get frustrated, or teachers who don't know the facts about brain development don't know that this is true. And P.S., it's 10 years for everyone, not just kids or teenagers. For all of us, our brains need 10 years to move information into long-term memory, and 10 years of using it, right? Not just 10 years ago I got somebody's phone number and I still remember it. No, 10 years of using it and keeping it alive in your short-term memory will lead it to move into your long-term memory. So if you don't know your multiplication tables, do not be ashamed of yourself. You'll get them. It just takes a while. Okay, I'm going to push in my soapbox. You know that expression? When I get, when somebody gives a impassioned speech, we call it getting up on your soapbox, right? It's like you're pulling out the old-fashioned wooden crate and standing up so everyone can hear you rant and rave. Sorry. I hope you enjoyed it. And I hope you should feel smart. Even if you don't know your multiplication tables, who cares? 8 times 7 is 56. You'll learn it. Okay, I'm done. Happy week 17, I think, right? We're done with 17? I think so. Yay! No, maybe is it 16 or 17? I'm going to answer that question. It's week 17. We finished week 17. Oh my gosh, we're making so much progress. Okay, goodbye.